Hello physicists, today we're going to do some review on magnetic fields, magnetic forces, and we're going to add in the idea of Faraday's law. Faraday's law, which tells us that changing magnetic fields can cause electric fields. So in our last video we reviewed our whole bevy of right-hand rules. We've got one for magnetic force where our finger is the speed of the particle. Our middle finger is the direction of the magnetic field, and our thumb is the direction of the magnetic force. We've got another one for the the direction of the magnetic field as it loops around a line of current. We have another one for the direction for our loop, our magnetic loop, where the direction of the magnetic moment is defined by our thumb when we curl our fingers around in the direction of the current. This also happens to be the direction that B is pointing along the axis. And then we had another one for Ampere's law, where it was helping us to define the direction of positive current if we were going around a particular loop for our loop integrals. So we've done a lot of this. I think it's time for us in this video to take stock and try to do some practice, try to make sure that we understand how to apply these rules and then push it forward. Because ultimately the place that we're going with this is that the electric field and the magnetic field are intertwined. A changing electric field can cause a magnetic field, a changing magnetic field can cause an electric field. And that dance is what causes, for instance, the propagation of light. So, okay, let's not get ahead of ourselves. Let's take a look at this problem. This problem I assigned you to try to think our way through some issues about the magnetic fields surrounding a long straight wire. Okay, so we have particles whose velocities are directed in different directions, and they are at different distances to the wire. So these ones are at, let's say they're at a distance of r1, and these ones are at a distance of, let's say, r2. Now, take a look at this picture, and the current is running from left to right. What direction would we expect our magnetic field in the plane of the page to be pointing? Okay, so when you do that, you have to put your thumb in the direction of the magnetic field and then point your fingers, and your fingers should be pointing at a right angle to the palm of your hand. And so in this case, in the plane of the page, our magnetic field would be pointing in. All right, so I have a B1 here, and it is going to be pointing into the page. I also have a B2 here, again, just pointing into the page, but our expression for the magnetic field strength around a wire said that it depends on R. So the farther away from my line of current I go, the weaker my magnetic field strength gets. So in this case, my B1 is closer to the wire, so B1 has a magnitude that's bigger than that of B2. Now let's look at the question. It says we've got an image that represents a snapshot of the velocity vectors of 4 electrons near a wire carrying current I. The 4 velocities have the same magnitude, velocity V2, directed into the page. They are electrons. 1 and 2 are at the same distance from the wire as are electrons 3 and 4. Rank the electrons according to the magnitudes of the magnetic forces on them due to current I, greatest first. So when we do this, we're going to have to use our Lorentz for our force law for vectors. So V is going to be the direction of our velocity, B is going to be the direction of our magnetic field, and Q is going to be our charge. Now, notice that Q is negative for an electron, and so we're going to ultimately have to reverse the direction. Okay? So let's try our V1. V1 cross B, my thumb would be pointing to the left, but since I would have it be an electron, I would have to reverse the direction and my force would be to the right. So there's my F1. Now, notice we've got a little bit of a weird one here for V2 because V2 is pointing directly into the page. B1 is also directed just straight into the page. So the F on that particle 2 is going to be 0 because they are parallel. The two ways that you can get a zero magnetic force are either to have zero velocity or to have your velocity vector directed parallel to that of the magnetic field. Okay, and then your F3, if I do my B2 would be into the page, V3 would be pointing to the left, so I would go V cross B, and then my thumb would be pointing down, but it's negative, so I've got to go the other way. So my F3 would be pointing up. And my V4, V cross B, so my thumb would be then pointing to the right, but then I would have to reverse it. So I would get a force, F4, that's going to the left. All right, now, because B1 is bigger than B2, our magnitudes here, if we're just talking about, consider these all as just positive numbers, my F1 would be V1, okay, it would be E, the magnitude of my F1 would be E times V1 times B1, where, you know, B1 is equal to mu naught times I over 2 pi R1, so that's a bit bigger. F2 would be 0. F3 is going to be E V3, B2, and then F3 is E, we're talking about magnitudes here, is going to be E times V4, or F4, times B2. So what you get in the end, because V3, V4, and V1 all have the same speed, you'd have that F1 has the biggest magnitude, is greater than F3, which is equal to F4, which is greater than F2. Okay, let's look at another example with a homework example from currents. It says, in this figure, two long straight wires are perpendicular to the page and separated at a distance D1 equals 0.75 meters. 0.75 centimeters. So this would be 0.0075 meters. Okay. It says wire 1 carries 6.5 amps into the page. So I1 equals 6.5 amps. What are the magnitude and direction into or out of the page of current 2 of wire 2? So we're looking for this. I2 equals question mark. If the net magnetic field due to the two currents is 0 at point P located at a distance 1.50 centimeters from wire 2. Okay, so this is 0.0150 meters. Okay, now, because I already know everything about wire 1, I could go ahead and stick in all of those numbers. I can stick in my I into this equation. I could also have an R. Now, keep in mind that for calculating my R1, that's the distance from this wire to the point that we're interested in looking at the magnetic field. It would actually have to be the sum of the two distances they gave us. It's not just D1 or D2. The R1 would be D1 plus D2. So essentially, the magnetic field contribution, if these both had a current of 6.5 amps, for instance, then you wouldn't end up having a zero magnetic field there because the contribution of wire 2 would be greater. So, in some sense, wire 2 is going to have to cancel out the contribution of wire 1. Now, if you use your right-hand rule, you can figure out pretty easily that the magnetic field from wire 1 is pointing to the left. So there's your B1. Hence, your magnetic field from wire 2, if that total magnetic field at that point is 0, remember we're adding magnetic field contributions like vectors, it would have to be pointing the opposite direction. Okay? So, if that's true, we know that wire 2 must have a current that's coming out of the page for our right-hand rule to imply that the magnetic field contribution at that point is pointing to the right. Okay? So we've answered our first question. Then we know that our R2 is equal to D2. And then we would simply need to set up our equations such that B1, or let me put it this way. Let's use our directions as x direction. So B2 minus B1 would be 0. So in this case, B2 would be mu naught times I2 over 2 pi, and then our R2 would be just this D2 minus, and then for our B1, it would have to be mu naught I1 over 2 pi D1 plus D2 equals 0. All right, now you could go ahead and solve for you would go ahead and solve for I2. Okay, so I'll let you do the rest of that homework problem on your own, but notice that all of the rest of these I have values for. I have values for mu naught. Mu naught is just that 4 pi times 10 to the minus 7th Teslas times meters over amps. D2 is distance, D1 is a distance, I1 is a current, and then I2 is the current that you're going to have to solve for. We already figured out that it's going to be coming out of the page. Now, something that's sort of implicit in everything we've said so far, but I don't think I've said it explicitly in any of these videos, is that if you have two currents, they can effectively pull on each other. And the way to think about this is that if you have two currents that are running parallel to one another, for instance, as in this picture, the first one is going to have a magnetic field, and then because the first one has a magnetic field, it can have a magnetic force that acts on the current that's running through the second. And the effect works backwards as well. So if you have a current through the second, it produces a magnetic field that acts on the first. So for instance, in this particular case, let's say that I had my magnetic field from A. You'd have B from A at that distance, at that radius of the distance between them, would just be mu naught times the current of A all over 2 pi d. Now, if you're looking at this picture, it would turn out that well, let's hold off on that for a second. So then that magnetic field is going to be pointing down, as in the picture. The current would be going as it's directed here, and then that would cause a force that would cause these two parallel lines that are flowing in the same direction to be pulled together. And so the magnitude of that, I would put in this magnetic field into there, and then the force on wire A would be due to the magnetic field of wire B, and I'd put in the current from A, the length of the wire, the current from B, whoops, and then, so I'm going to then just write it straightforwardly. I'm going to have I times L times B, mu naught IA over 2 pi d. And then I can just rearrange that to get the expression that's in your book. Okay, so I have mu naught times the length of the wire that I'm concerned with times IA times IB. Now, the interesting thing in this case is that that force is going to be the same on each case. So the force of BA is going to be the same as the force on AB. And so you can think of this as a Newton's third law type of action-reaction force, where they're equal and opposite. Now, this will help us to do one of your homework problems. You'll notice here we have a arrangement of four. We have long, parallel, equally spaced wires, which each carry equal currents into or out of the page. Rank the arrangements according to the magnitude of the net force on the central wire due to the currents in the other wires, greatest first. Okay, so I'm just going to number these 1, 2, 3, 4. And let's think about the forces. If two wires are going parallel, they pull together. If two wires are going anti-parallel, I'm using language a little bit loosely. If the currents in two wires are two parallel wires, if the currents are moving in the same direction, they will pull together. If the currents in two parallel wires are moving in opposite directions, they will push apart. The other relevant piece of information here is that because of the way the magnetic field scales, if two wires are close together, the force will be bigger than if they are far apart. So let's look in this picture. 2 and 3 are closer to that middle wire than are 1 and 4. So in this case, my big forces would be from 2 and 3. These are moving opposite directions. 2 is out of the page. The middle wire is the wire 2 has a current that's moving into the page. The middle wire has a current that's moving out of the page. So they are going to repel, and so the force from 2 is going to be in this direction. The force from 3 is going to also repel. It's going to be in that direction. 1 and 4 are farther away, so the forces that they apply are going to be smaller, but they are moving in the same, the current is moving in the same direction as the current in the middle wire, so 1 is going to pull it's going to pull this wire towards itself, so there's your force from 1, and the force from 4 is going to pull towards as well. Now you'll notice there are balanced forces in this case, so overall the force is 0 in that particular case. Let's just look at one more example where the force is not going to be 0. 1, 2, 3, and 4. So in this case, 2 F2 and the middle wire are moving in opposite directions, so my F2 is going to be pushing away from 2. My force 1 is also moving opposite directions, so it's going to be moving, it's going to push away with a smaller force. My F1 and F3 are moving in the same direction, so the middle wire is going to be pulled towards wire 3 with a large force. So there's my F3. And then my F4 is also, the currents are in the same direction, so F4 would also again be the same magnitude as F1, but pointing towards F4. So this is going to have F1 plus F2 plus F3 plus F4, big force because none of those forces cancel out. Okay, so I'll let you finish that one, drawing in those arrows and trying to think about the vector sums. Now, just to do a quick concept check, I know there's a lot of equations that are running around because we've done derivations and then we come up with a single thing. I'll have you notice that the equation for the magnetic field of a straight current carrying wire is given by this. Okay, so this expression is for a straight line of current. This expression is for the magnetic field right at the middle of a circular loop. Now the question here is, although these equations look similar, there's an important difference between these two equations other than the factor of pi. Okay, so the equations look the same, all that you're missing is the pi. And then if this were a quiz question, you might ask, what is it? Well, is it that the mu naught factor is different for the two situations? No, mu naught is an experimentally determined value, and it's almost exactly 4 pi times 10 to the minus 7th Teslas times meters over amps. Can't be it. The I also represents current in both cases. The difference is that the R is representing two different things. Let's take a look. In the first equation, if we have a long line of current, the R is representing a distance away from the line, and it can take on different values, and we can get different values of B at different distances from the wire. On the other hand, for this one, this is actually a sort of a simplified version of, you might remember, a more complicated version that we wrote down on this last time, which was mu naught times I times R squared over, let me think, I think it was something like 2 times R squared plus Z squared to the 3/2. Something like this. So the way that you go from this to that is simply by setting your Z equal to 0, and then you look at the magnetic field right in the middle. Now, the reason I bring this up is that the R here is not a variable. It's a constant that determines the geometry of the wire that you're dealing with, and then the B is also, it's just kind of fixed. The only thing you can really change there is the current running through that wire to get different magnetic fields in the middle. Okay, so the reason I bring this up is you do want to be careful because sometimes equations look similar for cases that are pretty distinct physically. Now, one of the other things that I just want to quickly review is that we've talked about current loops as a good way to generate magnetic fields. And so we came up with this magnetic dipole model where the magnetic field dies off as 1 over distance cubed away from this loop of current, and we define something called the magnetic moment that also tells us about the strength of that magnet in terms of its current and how big the area is. The other model that is important, and these are the two models that we test in lab this week, is that of the ideal solenoid. So this one has the assumption that we can figure out what direction the magnetic field is in its core using the same sort of right-hand loop rule as we could use for the individual dipole. But the magnetic field inside of that solenoid, which we consider to be somewhat long, is going to be dependent on mu naught, of course, the current. So the bigger current I get, the bigger the magnetic field, and also the number of turns per unit length. So they're secretly units of inverse meters in the denominator of that little n in this case. So I thought it'd be just worth us, for one, realizing that there are practical applications of solenoids. So for instance, if you've ever seen an MRI, they have an enormous magnetic field caused by high current, low temperature superconductors. And what's sort of special about this is that instead of having the same magnetic field everywhere, you get a secondary magnetic field that's pulsed. And because you get that secondary magnetic field, you can look at the rate of precession of the spin down of different materials within the body. Okay, so I encourage you to look up something about that if you're interested in it. If you're not that interested and just want to see some destruction, it is also interesting to see YouTube videos of people who put metal objects that are magnetizable in the same room as an MRI, and they sometimes fly across the room. So there can be drastic consequences, which are interesting to watch. Another interesting sort of application of this, if you have a differential solenoid where you have smaller current, bigger current, so you have kind of stacks of these magnetic loops, you can create a magnetic field that has a gradient. So it's bigger on the top than it is on the bottom. And it turns out that if you do this, you can cause magnetic levitation. And when I was in grad school the first time at University of Kansas, I heard a guy from KU MC in Kansas City talk about his experiment where they would put these rats in a differential magnetic field and get them to float. And they justified this, I believe, by saying they were going to help NASA talk about, anti-gravity stuff. But to me, it seemed like kind of a cruel thing to do, and then they would kill the rat at the end of the day. So anyway, that's part of my long journey to becoming a vegetarian. Anyway, all right, so let's make sure that we understand the relationship here. If we have a 200-turn solenoid having a length of 25 centimeters and a diameter of 10 centimeters, carrying a current of 29 amps, how would we use this equation to calculate the magnetic field inside of the solenoid? Okay, so if this is our part A, we could go ahead and just apply our equation as 4 pi times 10 to the minus 7th, that's mu naught in good units, times 0.29 amps, that's I in good units, times n, which is actually the number of turns per unit length, so it's 200 turns per unit length of 25 centimeters, so I'd have to put that in meters, 0.25, and this would give me a magnetic field in Tesla. So that's where I got that number out of. And then for part B, what is the magnitude of the magnetic dipole moment of this solenoid? So let's say that you go far, far away from this thing, and instead of treating it as a long thing, you instead are going far out, and now you're looking down on it, and it looks just like a bunch of loops of current. In that case, you could find out the dipole moment of this thing by just going the number of loops, so that would be 200 times the current in amps, so that would be 0.29 amps, times the area of the cross section. So that would be your pi r squared. So pi times, and our diameter is 5 centimeters, so this would be 0.05, the radius is half of the diameter, and then squared. And that would give me my magnetic moment in amps times meters squared. Okay, and so that's where I got this second number. Now, the last thing that we have covered in this unit, and we'll just touch it quick, is that sometimes you can solve the magnetic field in very regular situations with Ampere's law, where instead of worrying about all of the individual contributions to the magnetic field by integrating over them using the Bout-Savart law, you can instead do a single loop integral. So a nice example of this is a toroid. A toroid is where you take a solenoid and you wrap it around in a circle so that it doesn't have to be infinitely long. However, the magnetic field is not quite constant in there. If you make that Amperian loop through the thing, I mean, you can go inside or outside and realize that the magnetic field inside and out should be approximately 0. But inside of that loop, you'll get a magnetic field that depends on the radius. How does it depend on the radius? Well, let's do the loop at a particular radius. Then we can see that this side of Ampere's law would give us B times 2 pi r. And then here, my nu enclosed would just be mu naught. And then I would just have however many wires I have right there. It would just be N times I. Okay, so then I could go ahead and find out what my magnetic field is at a particular radius. Would be, so in this case, my magnetic field would be pointing always around like this at different points within that thing, and the magnitude would be mu naught times N times I over 2 pi r. So that's similar to a solenoid, but it's been wrapped in a circle, and we call it a toroid. Now, the new idea of this of today involves taking a magnet and shoving it towards a loop. It turns out that if you do that and you hook up an ammeter and measure the current, if you just have the loop there and the magnet there, the magnet's not moving, you check the current, no current. But if you start moving the magnet, as you're moving the magnet, you get a current. As you pull the magnet away, you get a current. Now, this is essentially a very simple form of sort of what's going to be our AC motor. Pull, 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 pull. You can get the current to go back and forth and back and forth and back and forth and back and forth. Okay, so Michael Faraday realized this, so he gets the credit for Faraday's law. What causes currents? Currents are caused by electric fields. So, changes in magnetic fields must produce electric fields. As we're going to find out, there's a parity to this such that changing electric fields also cause magnetic fields. Now, this is going to turn out to be even more interesting because if you take a loop of wire here and you, for instance, close this switch such that you turn this current on, when you turn that current on, it's going to create a magnetic field around that loop. But that's a change. So a changing magnetic field through this loop causes an electric field, and so you can go ahead and get a current here. Okay? So you have now induced a current with your changing magnetic field. And of course, if you open and shut this switch, you can go ahead and create an alternating current. And in fact, this is what we're going to do several weeks from now. So we're not going to do it quite yet, but you can use this to sort of explain how first, things like radios work, because you have to have an oscillating circuit, and eventually even how light propagates. Okay, so what is our rule here? Magnetic flux and Faraday's law. Well, magnetic flux is exactly like electric flux in that except we've replaced B with E. So instead of the electric field dotted with the area over a surface, it's the magnetic field dotted with the area over the surface. So the units of this, Teslas times meters squared, we give a new name called Webers. And Faraday's law tells us that the voltage around a loop caused by changing the magnetic field is related to the rate of change in the magnetic flux. Okay, I have to go to teach class, and I will be back and finish this video in a couple hours. Okay, so now I'm coming back several hours later to finish recording this video. And basically what Faraday's law tells us is that there is a voltage, so this is our integral of our E around the loop. Okay, that voltage is related to how the flux through the surface is changing. So it's the change in that integral over the surface of, maybe I shouldn't have a circle on there. It's not a line integral, it's a surface integral of B dot dA. Now, for those of you who have done the whole vector calculus thing, you'll recognize that this is related to the Maxwell's equation that looks like this. The curl of the electric field looks like the changing magnetic field. Okay, so changing magnetic field causes an electric field. So just to put a check on this, if you have an induced voltage, it depends on the rate of change of the magnetic field, not the size of the field. So here's a check. If we have a magnitude B of the uniform magnetic field that exists throughout a conducting loop with the direction of the field perpendicular to the plane of the loop. Okay, so we've got like a loop here, and we've got a magnetic field here. The magnetic field, we consider that maybe this is inside of a solenoid or something like that, and we're going to measure the voltage. Now it says rank the 5 regions of the graph according to the magnitude of the EMF induced in the field loop greatest first. Now what we're trying to get across with this question is that the EMF is related to the change of the flux, not the size of the field. So for instance, this would be the biggest change, this would be the next biggest change, and then this would be zero change because the magnetic field is constant. So it doesn't matter that the magnetic field here is big, it just has to do with the rate of change. And so in here, your V in the voltage induced in B is going to be bigger than the voltage induced in D, which is the same as the voltage induced in E, even though the magnitude of the field is bigger in section D, and that's greater than the voltage in A or the voltage in C, which are both going to be have a size of 0 volts. Just to do a more numerical question, it says here's a homework practice problem that I assigned. It says the magnetic flux through the loop increases according to the relation flux through is related to T squared and T, where the flux is in milliwebers. Okay, So here, to get the flux, it would have to be 1/1000th to get it into Webers, 6t squared plus 7t, and t is in seconds. Okay. Then it says, what is the magnitude of the EMF in the loop when t equals 2 seconds? Well, you could go ahead and take your d flux dt, and it would give you 1/1000, and then this would be 12t plus 7, and then I would just need to put in 2 seconds right there for t. Okay? Okay, so then just multiply that out, and that should give you an answer that is in volts. Now, the second question asks, is the direction of the current through R to the right or left? Well, the induced field, the induced magnetic field, is always opposing the direction of change. So the field is getting bigger coming out of the page. So the field that is induced is actually going to be going into the page. We'll talk about this more in the next video. So B induced is going to be going into the page. And so if I look at the direction that that implies, that would imply that around this loop, the current would be going this way, this way, this way, this way, this way. And it's going to be going the same in all the directions. So the direction through that resistor, I would be going from right to left. Okay, it's going over like this through that resistor. Now, just to look at another example of this, it says we have a metal rod forced to move with a constant velocity along 2 parallel metal rails connected with a strip of metal at one end. A magnetic field of magnitude B equals 0.350 Tesla. Okay, so they give us the B, and it's not changing. Points out of the page. If the rails are separated by a length of 25 centimeters, so that is not changing as well. And the speed of the rod is 0.25 meters. The speed is 55 centimeters per second, so the speed would be 0.55 meters per second. What EMF is generated? Okay, now, to do this, we need to first realize what is the flux. The flux here is going to be the magnetic field times the area. So it's going to be times that L, which is not changing, times this width, which is changing. So the area that we're talking about is that area, and we're thinking about the current around, or the voltage around this loop. Now, if we're going to look at the change in that with time, B is not changing with time, L is not changing with time, so it's essentially going to be B times L times the change in that width per time, but that turns out just to be the speed of that bar. That's how much that width is changing per time. So this is just going to be B times L times V. Okay, so the EMF is related to this, so I can just take in the B, 0.350 Tesla, times L, 0.25 meters, times V, 0.55 meters per second. And so if I take Tesla times meters squared over seconds, that should in fact give me volts. Okay, and then part B asks, if the rod has a resistance of 18 ohms and the connector, rails and connector have a negligible resistance, so this is turning this into a V equals IR type of question. So you know V from this part, this EMF would give you your V. V equals I times R. They give you R equals 18 ohms. And then they want you to find I. So you could do that. Maybe just to be clear, let me just, this funny looking E is IR. Okay, so here you found the funny looking E. And then in part C, it asks, at what rate is energy being transferred into thermal energy? Well, remember you had power equals I times V. So in this case, the V is that EMF, so it'd be P equals I times E. So you know E from the first part, you know the voltage that's been generated, you know I from the second part, so you can just multiply those together and find it. Okay, so that's enough for today. We learned that parallel currents pull on each other because each of them responds to the magnetic field of the other one. We learned that changing magnetic fields can induce electric fields with a voltage proportional to the rate of change of the magnetic flux. And we're going to need to do a little bit more practice with that. So in our next video, we're going to work on practicing that with something called Lenz's law to help us figure out the direction that the voltage is directed. Okay, so thanks for watching, and we'll be back soon.